Okay, hey everyone, welcome back to our security table podcast here at Olympix. This is our second episode. We're kind of digging further into our series on audits and kind of why they are not foolproof, why audits aren't enough. Today we're going to talk about protocols that have been audited and yet exploited. We're going to dive into some tangible, real examples. To show you that even audited protocols can and do get exploited all the time. So we'll talk about hacks ranging from tens to 100 million in the past few months that have all taken place on audited code bases. We'll explore some of the kind of mechanics or the attack vector behind each hack, how audits missed them, and what that kind of means in real terms, and also why they were preventable, and how teams can kind of move forward to prevent these types of exploits in the future. And so, yeah, long story short, audits are necessary, of course, but they are insufficient for evolving systems under real world pressure. So, bit of context to set the scene. And this is, of course, why Olympix exists, but hacks are happening in spite of audits. They have been happening in spite of audits. Hani, tell us about what was going on when you started Olympix, and what is still going on now.
Yeah. So, for context, I started Olympix because transparently, I'm an engineer and the attack surface was very interesting. And at first I thought, well, with such a crazy attack surface and such unforgiving consequences, i.e., your entire protocol can get drained, there must be the most incredible technology being built here. And the more I looked, and this is kind of what leads to the genesis of Olympix, the more I realized there wasn't. The sole reliance for security was the manual third-party audit, which of course is important, but it is not foolproof. In 2022, when we started, it was about 14 billion exploited, with 90% of that undergoing the manual audit. So the whole genesis of Olympix was like, can we, one, automate parts of what they're doing? And two, can we find things they miss? And if those things can be true, then we will be successful and we will further the ecosystem. We'll help developers own security, have autonomy, decentralized security, help the auditors even, because now the auditors have more time on their hands to find more novel attack vectors. Like, a lot of pressure was put on the auditors by making them the sole source for a security posture that is such high consequences and you can't afford to be wrong. So yeah, that's a little bit about like the market and where it was in 2022. As of today, it's only grown in terms of not just market size, but exploit size, right? They grow together in parallel. And you have to just think of incentive structure here. So the more money in your protocol, the more badly North Korea wants to exploit it and pull that money and put it towards their nuclear program, right? So as our market continues to grow more aggressively and more aggressively, which we're seeing so much of with the institutional adoption, this will only hold true even more so, yeah.
Yeah,
I think
absolutely.
this year alone, like, we're projecting around 5 billion in losses.
Yeah, it's definitely they're the two are correlated, and it's also a huge barrier for further institutional adoption or for the further capital flowing on chain. So
Yes.
a big thing that we want to put a stop to or help to put a stop to, and as you said, further the ecosystem. So today on this episode, we're going to talk about six hacks from the past approximately 1 year that all took place on audited code bases and kind of for different reasons and preventable in different ways. So we're going to talk through the 1-inch hack, Penpie hack, Hedgey finance hack, Cork hack, the Paxos PayPal not hack, but kind of issue or stablecoin minting issue, and then the Balancer hack, which was very recent. We would be reticent not to talk about Balancer. But I'll hand it over to Anish, our resident technical expert here, to dive into the 1-inch hack first. So yeah, Anish, what happened there?
All right. Yeah, thank you, Sarah. So for 1-inch, they had the Yule call data corruption. We saw a hack actually very common in Web2, which was the buffer overflow attack being replicated here in Web3. What they had was they had an underflow in one of their Yule statements for a caller controlled value, and that's what led to the buffer overflow. Our static analysis could actually have prevented it. So it was not that sophisticated of a detection of an exploit mechanism. We have seen this attack, as I said, over and over, repeated everywhere. All you had to check was for that there are no possible underflows in that Yule statement.
And why do you think that this is something that an audit might have missed, given that it is not massively sophisticated?
Sure. So a couple of reasons. One, Yule just is hard. given the complexity of Solidity, and then now you have to look at Solidity as well and understand the EVM ecosystem. That's not super easy. It was also finding out that this was actually caller control. This was not, which was not really apparent, and that's why a human order might not want to look at that call flow. They just trusted that this variable would be safe enough. So yeah.
And what makes it easy then for specifically static analysis to pick this up?
Sure. So we don't have these bad biases, right? Like we don't assume anything about that piece of code. It might or might not come from the user. We have no like bad heuristics essentially, which these human auditors might have developed.
What's your sort of recommendation for teams that might be listening to this and going like, okay, I need to keep my eye out for this, maybe that don't already have a static analyzer, a good static analyzer in place? What's your recommendation?
My recommendation is you get the Olympix static analyzer. And yeah, I really think that Olympix static analyzer should just be the Olympix static analyzer should just be table stakes for any company that's even trying to operate in the Solidity E/EVM ecosystem.
Let's talk about the Penpie exploit. What happened there?
Sure. So they had a reentrancy, which is a word we keep seeing over and over again, right? In Solidity. In fact, there have been reentrancies all throughout the year up till last month. So reentrancy is something not to be ignored about, or something to forget about. For Magpie specifically, what they had was they were lacking a non-reentran modifier in one of the functions, and there was one particular branch that they never thought would trigger that reentrancy, and that function needed that modifier. Our mutation testing would have prevented this hack from happening because it would have told the team that there's no validation for example, reentrancy being done on all these functions.
And again, same question, why did the audits not pick that up?
Sure. So as I said, there was only this one branch which would have caused this reentrancy to happen. Finding that exact branch is again not possible for a human. When you are looking at the code as a human, you don't really think about all the permutations and combinations of the branches that might exist. And in fact, it's not humanly possible to do that over and over again for all these functions. That's why I believe in automated tooling that can detect stuff like this.
And why is mutation testing specifically the tool that could have flagged this?
Sure. Mutation testing is the most direct tool that could have flagged it, while the other tools will also point out problems in there. But directly, what this had to do was with this change of modifiers, right? So there was this lack of modifiers, and there was this incompleteness in the test suite which detected this lack of modifiers. So what mutation testing does is it points out those holes in your test suite that might talk about improper validation of your source code, and that's why it will directly say that you're not validating for example, reentrancy risk in these functions. And yeah, that's how you would have seen the hack.
And I know from our dealings with prospects, with customers, mutation testing isn't really commonly adopted because it's massively time consuming to do manually, and there aren't really other solutions that exist for automating mutation testing. But for people that are listening and going like, okay, cool, I'd love to have something like this in place, but I actually don't even know what mutation testing is. Can you give a little bit of an explanation just on the sort of like thesis behind mutation testing, and then what Olympix does to automate it?
Sure, of course. All right. So the main idea behind mutation testing is we introduce small changes in the code base. For each change that we introduce, we'll run your test suite. What we expect is your test suite should start failing after we introduce any change. An example of this would be, suppose you have a super important function somewhere and it's protected by the only owner modifier. I'll go and I'll remove that only owner modifier. What I expect is your test suite should now start screaming at you. It should say that there's no access control on this super important function, right? And you need to know about that at compile time, at testing time, not during deployment or after deployment. Right. So this is what we assert throughout your entire code base, throughout all of your contracts, and we systematically do these changes across all of them. Right. So you don't have to manually make these changes or even run it on your compute. We in fact consume all this compute. All of this runs on our servers. We do all the different testing, mutations, etc. You just get a clean report at the end telling you which mutations were detected or which of them survived through undetected.
Amazing. And I know, Hani, you've been working with many of the security engineering teams within the biggest protocols, biggest teams in Web3 for years now. We've had, teams that we've been working with since we were in MVP stage of our product and kind of all the way through the maturity.
Right.
Hani, you have said before that this is a favorite tool for security engineering teams. How do
Mhm.
you see them kind of leverage it, and why do you think it is so impactful for security teams?
Mutation testing.
Yeah.
It's really interesting. It really depends on the buyer. Majority of our teams utilize the whole suite. However, when you get this really, really dedicated security engineer who's comes from a deep security background, oftentimes they either have heard of mutation testing in some capacity or it's a net new concept to them. And when they hear what it does, it clicks. And they're like, wow, I can't believe we didn't enforce this metric. And when that happens, it's a different story for them because they're able to actually quantify their risk and the security risk of their test suite, which is something they've never historically been able to do. They've only been able to eyeball it. They always knew that branch coverage wasn't enough, but they're like, okay, let's just get to 90, 95%. But, God forbid I am missing a test. There's no way for me to find that or look for that except for laying in this mind map of my own that I'm just gonna keep bumping things around, but there's no way to actually quantify it and test it easily until the Olympix tool came into their CI/CD pipeline. And once it did, it completely transformed how they write tests and how they do their development process. And so, Sarah, you often split this up for teams like, okay, this is pre-development and this is during development and this is pre-audit, which is the pre-audit, they're running the bug poker, which is the agentic system that uses our deterministic feedback. But before you even get to that, how are you internally during development utilizing tools? And I think that shift has been really helpful. Static analysis isn't novel. We just did it the best, which is like whoopee good for us. It was hard and annoying to build. It was honestly pain. And it's helped a lot of people, but it's not like something they haven't seen before. They were just waiting for that. They're like, okay, great, a good static analysis, sign me up. But when they hear mutation testing, it's like, wow, I can do that, and it works easily. And you see that with, like, for example, Uniswap Labs, that tool. Who else is like super security oriented? Like the Agora team loves that tool. There's a lot of great teams who
Wi-Fi, Magpie.
yeah. Oh, Li-Fi loves it. Yeah, yeah, exactly. Okay, there's just a lot of great teams who really have an appreciation for security metrics and they really want it to be part of who they are in their DNA. And when they start that during development, it obviously gets my little antennas excited because we love security oriented engineers. We love teams that hold the same mission that we do and like what we spend every waking, breathing hour focused on, which is deploy secure code at scale and allow this ecosystem to grow as a
I
result.
think
Yeah.
that's a great segue. One of the things that you mentioned was that the ultra security minded folks have been trying to sort of do this maybe with their own mind map, maybe sort of like semi-manually. But there is another layer or a next level of security that the most security-minded teams are trying to achieve. And one of the ways that teams seek to achieve that ultra assurance, ultra sort of mathematical verification of security is formal verification, but it is really, really challenging to do effectively. We'll come back to how we kind of help teams tackle that, but I think a good opportunity to talk about the Hedgey finance exploit. And Anish can kind of walk us through that because that was one that our sort of another one of our more robust, more kind of like security focused tools would have helped prevent. But let's tee it up and talk through that exploit.
Sure, yeah. Hedgey Finance was an interesting exploit. They essentially they had a particular code path in there which was a faulty code path which led to the hack happening essentially. What happened there was they would give the user certain an approval of some ERC20 tokens. They would transfer the money over to the ERC20 tokens. But there was exactly one code path. If you create a campaign and then cancel it, they would not clear that approval. So the user could hypothetically keep withdrawing more and more and more, and that's what the hacker did. And this is something our fuzzer/formula verifier would have detected by actually exactly finding those paths and enforcing that invasion and trying to break that.
Tell me a bit more about formal verification, how it sort of works in its purest original form, and then also fuzzing, how it works it kind of in its purest form, and then how we've married the two with this tool.
Sure, those are like two completely separate domains. The first thing, let's start with formal verification. Okay, what it says is that your code essentially is math, right? Like your code is a bunch of logic statements. There's a bunch of state transitions that's happening. There's an input, there's processing, and there's output. Now, in all these different code paths, or like different ways to the code that you can find, you can create different sets of math operations in each of these paths and get all these state transitions. Now, what formal verification aims to do is it will create rules, or like formal rules around all these in a particular language, which is whatever the spec language you might be using. So essentially, we have this math problem of turning this input to the output, and now you're enforcing rules on top of this math problem. So you're saying in all these different possible code paths, you have one rule. One rule might be that the total supply should never go to zero. That's one invariant that you can enforce. One invariant could be that no one user can own more than 51% of the shares of this company, like something like that, right? Like you can enforce any sets of rules over any math problem. And formal verification just makes sure it verifies that all these rules are being followed by all these code paths, and you can prove this mathematically.
Okay, so that's formal verification. Why would teams not then just use formal verification?
Yeah, sure. So ideally, everyone would use formal verification. Is again just come down to resources. It's very hard to write good specs for multiple reasons. One, you just have to learn a completely new language, which is not a part of your job description, right? So this takes a lot of time itself. Then actually thinking about these invariants is a hard process. It's not very apparent what all the invariants of any given protocol, DeFi system, etc. are. It's often a learning process that you'll learn over time, and even then you won't have all the invariants. So engineers will often have incomplete invariants or wrong invariants. And having these wrong invariants is even worse than having no invariants, because then you have this false sense of security that would actually lead to the hack, right? So that's like those are some of the few reasons that that creates like a lot of friction in teams even starting to do that, and often just hire a third-party service to do this for them.
And Hani, this, I suppose, like static analysis, this is not novel, right? Like this is not a novel type of testing to Web3. What
Formal verification?
Yeah. So what inspired you to try to bring this over to Web3? Like what had you seen in other spaces? Why formal verification, and why, I guess, trying to do it in a different way than it is currently done?
Yeah. So I'll touch on those 2 points. So one, I think it comes back to like my obsession with mission critical code. I think it's super interesting when your code gets hacked and something catastrophic happens. It's just like a more interesting technical problem. That's the gist of it. And you know, Anish and I share this just like urge as engineers to go after the like most difficult problems. So I've always been enamored with this type problem. So like to give other examples in other industries like medical device security. Okay, your medical device is compromised, could be life or death if it's, you know, the pacemaker of a president or whatever. Then there's aerospace, right? Your airplane, your rocket ship needs to be tested very rigorously because that software cannot fail. It's just hundreds of millions in equipment. Forget the human life. I don't think that's like their number one priority. I think it's actually the equipment. So formal proofs were always implemented in these two domains. Now, the way they were implemented is the same way that people historically have implemented them additionally in crypto, because again, it's catastrophic, mission critical. In the event that something goes wrong, your entire protocol is drained, i.e. your company goes down. It is not something small. It is the life or death of your company. It's your money, it's institutional investors' money, it's retail money, right? There's a lot going on there, and it can be in the magnitudes of billions. So the kind of historical way, which is what Anish outlined, is you learn another spec language and you implement the right spec. So this infers two things. One, that the engineer has enough time to learn a second language. And two, that they're smart enough to write the right specs, which actually infers that they're like in the 0.01% of smartness, which I just think is delusional to assume. You're going to see across the board and at scale. So these two things were just delusional to me, but I loved the verification aspect, and I believe it's the right approach that you need to deterministically solve in spaces like this. Like there is no room for probabilistic testing. It needs to be deterministic. You need mathematical assurance, which is like going back to mutation testing. It gives you that assurance that you tested things. And so we spent so much time in the research lab trying to figure out, and I think it's a question to also like hand back to Anish on kind of our solution from a high level. We won't give out our secret sauce, but on the research lab, trying to figure out how do we one click not only deduce like what's going on in the code, every single code path, look through that, but also what specs need to be written and how do we auto write them for you. So essentially one click, 1, 2, 3, and you're shipping. How do we set you up for that? And we've been very successful in that so far. Our tool is in private alpha, but we found some really interesting bugs so far and want to continue to grow it.
Yeah, so Anish, talk to us about the kind of Olympix and touch on fuzzing, I guess, as well, because we did say it's formal verification, automated formal verification, but it also is in part kind of
it's
fuzzing.
formal methods, which is like symbolic execution, fuzzing, formal. It's all like in the math category.
Yeah,
Sorry,
sure.
Anish, I'll let you talk.
No worries. I've been thinking about this for a bit now. Whenever we talk to people about mutation testing or fuzzing, it's kind of like talking about meditation with them, in the sense that they feel like, oh yes, I really want to I really want to do it, but I just don't have the time and effort to do it. And it's really hard for companies to start doing this, right? So what is fuzzing? Fuzzing takes the opposite approach to formal verification. It says that proving stuff is very hard, right? Like proving all these different code paths is impossibly hard. What we should do instead is you should still have these rules and invariants that my total supply should never be 0, for example. But instead of trying to prove it, what I'll do is I'll throw a bunch of inputs at it, and I'll statistically try to prove it. So if I give it enough variation range of inputs, and I'm still following this rule, observing this rule, then it's probably secure against this rule, right? This invariant is probably true. And I think Hani actually showed me some research paper showing that fuzzing approximates formal verification very well, actually up to a 90 to 95% confidence. So that's the other part of it. Now, why would a company not do it? Again, the problem is that you still have to write this invariance, which often again ends up being in another language. It's again the same amount of effort to write these invariants. The problem of the solver, instead of proving to these like various tries, gets easier. But for you as the engineer, writing these invariants is still impossibly hard sometimes.
And so at the highest of levels, what is our tool doing then to sort of combine those two things?
Of course, yeah. So what we did was, as you said, we tried to marry these together. Our job was to make this super easy, one click for the user. The user does not anymore need to think about invariants. They give us their contracts. We figure out everything that needs to be done, all the invariants, all the fixtures, everything. We figure out the right inputs, and then we write those fuzz tests for them.
Amazing. Let's talk about the Cork hack. What happened there?
Sure. So there were a bunch of components in there. There were two major parts. One, there was a very complex economic vulnerability that we can go into, but I don't think it's in the scope of this podcast. But Cork has an amazing blog article that you can explore if you want to look at that. The other part of it is that they had a hook. They had a Uniswap v4 hook, and in that hook there was one particular function that had no modifiers, right? So there was no access control baked into that function when there should have been. So the Uniswap v4 docs said that they should have used this particular hook in or this particular modifier for that hook, and if that hook was present, they could have prevented that hack from happening.
And why were audits not able to catch this vulnerability?
That's a hard question. I would think it's just within that human error, right? There's so many functions in there. There's so many modifiers in there. Trying to think through all of these possible cases is again hard. And Uniswap v4 hooks were a very new category, right? Like Uniswap v4 just came out. These hooks were not as common. Cork was one of the first few hooks that was actually audited by these companies, so they didn't have any heuristics developed around it.
Yeah, and an auditor, by the same token, is not a machine that can abstract code and go through every single code path and test it in certain ways the same way our tools can, right? They just don't have that capacity. Now, do they have capacity to do a lot of things that a machine can? Of course, and both are critical. But to think one is enough is to be delusional.
I think the point that you make there, Anish, about the like novelty of the V4 hooks is a really important component here, because something that auditors use to kind of help them increase their efficiency is essentially a checklist. So what are the, categories of known vulnerabilities that we can flag first as kind of the low-hanging fruit, and then I'm going to do my best with the remaining time that I have to potentially figure out some, novel or sophisticated vulnerabilities. But if this vulnerability class is not in those checklists, or if you're using something like an AI security agent or an AI auditor or whatever, if this type of vulnerability is not in the data set that the LLM is trained with, there's a high likelihood that it's going to be missed. In the auditor's case, maybe the auditor could still find it if they just happened upon it. In the case of the LLM, it's probably not going to find it at all because it just doesn't know what it's looking for. And so that's an interesting thing when we're talking about the sort of formal methods and the different things that underpin the Olympix tool suite. It gives us the ability to find vulnerabilities in all sorts of different ways that kind of go above and beyond some of the limitations and inherent limitations with different types of security services or security tools. Again, to Hani's point, like nobody's perfect. We're not implying that we're replacing an external auditor, but tools are really good at finding certain things. People are really good at finding certain things. You don't want to be caught in a position where you have deployed something that tools could have caught because you can leverage the tooling. The tooling does exist. And tell me, Anish, then how is Olympix able to catch this type of vulnerability that, was difficult for, I think it was 3 external audits to find in the case of Cork?
Sure. So the main reason behind this is that we have a lot of infra built around trying to understand this code. So for the longest time, that's been our main goal. In this process, we have built our own IR, or intermediate representation of your code base, that I think we talked about last episode. Essentially, what this helps us do is that it really helps us understand what the different flows in there are, what the different types of functions exist, how does data flow within these functions, how does ERC20, etc. flow throughout these functions, and that gives us a much bigger and wider picture of what it means, for example, to miss a modifier in here, right? And combined with this, again, as Hani mentioned, it's a machine, right? So this machine can really deeply and strongly look at all these different parts, and within a very fast, very small amount of time, make all these checks happen, right? And like that's what allows us to do this.
Amazing. Let's talk about, because it was so recent and so big, and I think so surprising for many reasons. Let's talk about the balancer hack. So, what went wrong there? And I suppose it's beyond just an audit missed a vulnerability. There are kind of multiple layers here because it was an old code base. So talk to us about what happened with balancer.
Okay, so they had a all right, start. So they had a mismatched rounding direction in the withdrawal process. Essentially, when they should have they should have had rounding that should have favored the protocol, they accidentally favored the user. Now it's interesting to note that they already had a comment in there noting this, that they know that this is bad and this would lead to a one-way approximate difference in that transaction. So they decided to ignore it. The problem came in when they had a token which was leveraged by the liquidity of that pool. So what that means is that because of the changes in liquidity of that token of that pool, the token price also changed. This allowed the hacker to compound these one-way differences. So essentially, this person called this a million times, right? And a billion times, and one way kept going up and up and up and up, and that's what led to the original hack.
And why do you think this was like acknowledged, I guess, and like left as okay? Why did they think, or why did auditors who looked at this think that this would not be an issue down the line?
Sure. So I'm also speculating here. We don't have information about this, but I would think that it was not known maybe that there would be leverage tokens which would allow this to happen. It was like it was not possible to probably compound this is what I think. It could also just be possible that no one thought enough about like if there are leverage tokens, how would this react if you try and intercouple them.
And so, interestingly, it is kind of similar in some ways to the Cork exploit, where it's like, not that it was a novel vulnerability itself. Obviously, it was like a known vulnerability. They flagged it. They were like, "Oh, it's all good." But what made it exploitable was something new that they didn't think of at the time when they introduced this potential vulnerability. So they said, comment, acknowledge, all good, leave it there. And then many, many years on, they introduce something that interacts with that contract and it creates a vulnerability. And of course, you're not going to go back and re-audit these audited contracts that you had deployed safely 3-4 years ago. But if you have tools in place, you can very easily re-audit the entire code base and all of the different contracts that are going to be interacting with one another. Obviously, economically speaking, you would never do that with auditors. You'd bankrupt the company if you tried to go back and re-audit every single line of code every single time. But it is this argument for like novel surfaces and novel attack vectors are emerging all the time, whether or not the original vulnerability was novel or not, whether or not you're interacting with a new surface, like whatever's happening, there is change, there's flux, there's evolution happening in the space. And if you're relying on a single fixed point in time audit that audits a set scope of your code base, you cannot be future proofing. You cannot be protecting against all eventualities. So very interesting for that reason. And how could Olympix have flagged that, or how was this sort of preventable given the context?
Of course, sure. So Bug Poker actually did realize that there was this leverage token that was that could compound this vulnerability. So even though we ran on a decompiled piece of code where we did not even have this comment, we could still see that. So we could still see that there was this one-way problem there, and there's ways to compound this with batch execution, etc.
Interesting. Okay, not a hack, but something that came up relatively recently, very interesting as well. Again, as Hani mentioned earlier in kind of what she had seen in the space early on, and then the evolution that we've been seeing in the space with more institutional money coming on chain, et cetera, et cetera. We're seeing big players in fintech like PayPal who are launching stablecoins, and they are working with, infra or tokenization or stablecoin providers within Web3 to help them do that. What happened with the Paxos PayPal $300 trillion stablecoin minting issue? How could a company, presumably as security oriented as both Paxos and PayPal, how could they both have overlooked something that would be such a kind of like ridiculous flub?
Yeah, so from what we know, it was just a fat finger mistake. There was just not enough validation on the minting amount. Some minter somewhere, some last manager somewhere just probably put in the wrong number in either the script or just their wallet, and this led to this huge minting issue. How we would have prevented it is that both our static analysis and our poker tools would have told the user that there's no or not enough validation for your minting amount. So there are cases like this possible. So we'd always suggest you that you should have double, triple validations on different parameters for all of your parameters of your external functions.
And Hani, when you're working with teams that are coming over from Web 2 into Web 3, whether or not they're building, internally writing their own smart contracts, or in the case of PayPal, they are working with a partner that is sort of crypto native to help them do that. What are some of the sort of challenges that you think institutions have when they're kind of stepping into a new territory or new paradigm in Web 3, and like how should they be thinking about security as they enter this new ecosystem?
Yeah, so I think it's split into two things. There's what is known, what they know to be true, and what they don't know. And so what they know to be true is traditional tools need to exist on top of third-party validation of your security posture. This is something that's mandated very aggressively already on the Web 2 side of things for them. So they know that to be true, whether it be static analysis, unit test, a certain amount of branch coverage, something like that. And then it gets to what they don't know. They don't know that they need mutation testing. They don't know that they need fuzzing, automated, formal verification tools. They don't know that they need that extra layer even though they understand the attack surface is larger. And so that's an educational gap. But what we can often do is start them on the earlier tools and then lean into that as we get them comfortable. But I don't see that changing for the foreseeable future. I think it's just going to be the education gap. But the nice thing is, it's almost the opposite of the Web3 native teams who only know that they need the more aggressive tools and don't know they need like the static analysis, the more basic tools. So it's like they're the opposite, and there's education on both sides. Yeah. But it's good. They're used to tools. They know how important it is, and that type of mindset and culture is already embedded within their orgs. And so it's easy to just show them the results and the value, and they'll purchase from there.
Yeah, it makes sense. And I think given everything that we've shared so far about the sort of formal methods that underpin everything, these existing best practices that kind of come from Web 2, the new pieces that we're introducing for Web 3, Olympix is sort of uniquely positioned to be able to service these types of organizations that are moving on chain, because they are going to expect the rigor that they have already established in sort of the Web 2 development process. And only formal methods are going to be able to help them achieve that rigor. That's sort of like auditable, verifiable. And when we're talking auditable, of course, not just external third-party auditable, but like audit trail, verifiable, compliance grade security. Compliance isn't there yet. Regulatory isn't there yet, but you can rest assured that it will be in the coming, years. And it will be mandating these types of tools that are already mandated in Web3. And so building on a foundation of sort of formal methods and deterministic methods as we have means that we are ready to serve them with the tools that they're used to, but for this new paradigm. So I think takeaway overall here, we've gone through a ton of top protocols, top organizations across the space who have all followed the existing best practice, which is getting an external third-party audit or multiple, and they've still undergone a hack. So quick recap here, we had 1inch, we had Penpie, Hedgey, Cork, Paxos, PayPal, Balancer, all audited code bases, all major hacks or issues that were able to be deployed and exploited in some way. So it's another reminder that an audit alone or multiple external audits alone are not foolproof. You do need a Swiss cheese redundant approach in security. You need proactive to be that first layer. You also need layers within the proactive. So just to have one proactive testing methodology or one proactive tool is not enough. You need that layer of static analysis, unit testing, mutation testing, fuzzing, formal verification, and then some combination of all of those things that kind of powers your internal audit. But again, leveraging these kind of formal methods that are tried and true, battle tested in mission critical industries where a lot is at stake. And just a reminder that audits are important. We are not saying that they're not important. Human beings are really good at finding certain classes of vulnerabilities, but tools are also better at finding other classes of vulnerabilities. So if you've got the capacity or the capability to find those vulnerabilities yourself with tooling for the fraction of the cost of a single external audit, and then that's infinitely scalable across development life cycles, across audit cycles, why wouldn't you? Why wouldn't you implement that tooling and clear away as many vulnerabilities as possible before you go to external audit, so that that audit can be more effective and more fruitful, and you can be more confident in the findings. That audit is exhaustive. There are fewer findings, which signals to your stakeholders that you are writing very secure code when you publish that audit report, and there's just a couple of lows. And then, of course, more importantly, as we kind of look through the examples that we've just outlined here, you can catch things that audits miss because they're not foolproof. And that, of course, was the whole point of this series. So thank you for joining us for episode 2 of the Security Table podcast, and we can't wait to see you for episode 3.